Ma, are you able to hear my voice clearly, right? Dear
Yes,
students.
sir.
Okay,
Yes,
no, no,
sir. Yes,
no,
sir.
no problem. Okay. Last class, I have left with this one small topic here. I will cover this one and we will move on to the half a dipole part. Okay, can anybody tell me what is the equation for directivity? Okay, the equation for directivity is D is equal to maximum radiation intensity divided by the average radiation intensity. Okay, how to get the maximum radiation intensity? This is nothing but, okay, here the average power or power density multiplied by r square. Okay, we already know this one. Okay, if you have any doubt, please go back and refer that topic. Okay, here D is equal to maximum radiation intensity divided by the average radiation intensity. Okay, this is the equation for maximum radiation intensity, and this is the PR, is the total radiated power divided by 4 pi. This gives the average radiation intensity. Simply, we have already derived P average and the total radiated power. Just to substitute here, okay, we will get the directivity. Okay, in any antenna, okay, if you know the average power and the total power, we can calculate the directivity. What is the capital? What is the R here? R is the distance where we are measuring. This is the observation point. Okay, the distance between the observation point and the source. Okay, this formula is same for all the antennas. Okay, for short dipole antenna, the average power equation is this one. Okay, here we want P average into R square, right? That's why this is the P average. This R square I'm taking this side, I'm getting this one. Similarly, the total power is, we have integrated over the entire sphere of this average power. We'll get the this total power. Okay, this total power is equal to, we are getting this equation from where you are getting this equation from here, right? See, here is the average power. Here we can write this as a eta naught. That is the intrinsic impedance. Okay, and we have calculated the total power. Here we are written P. Here also have written P here. Okay, finally I have say change it to PT. Okay, you can the T indicates the total power. Okay, if you want to remove that, it is not okay. You can remove that also, no problem. Okay, similarly here also. Okay, okay, actually this P indicates the total power. Okay, I will change here also. Okay, this is the total power. Okay. Okay, by substituting this, actually this is the power equation. Here we are substituting this is the IM, maximum current, in terms of RMS. We'll get we are just simplifying the substituting all these terms, eta naught and IM in terms of IRMS. Okay, that's why I'm taking the two equations. Now here I have mentioned PT, no problem. PT indicates total power. Okay, therefore here also the total power divided by 4 pi gives the average radiation intensity. Okay, now, okay, D is equal to, now subtract these two terms. If you subtract these two terms, we will get 3 by 2 times of sine square theta. Okay, here this is the maximum. Here it is the maximum radiation intensity. But for the maximum radiation intensity, okay, this is the average power multiplied by R square will gives the maximum radiation intensity. That's why you have to take the here this theta also maximum. Okay, when what is the maximum value of the maximum value of the sine square theta? This value is 1. That's why, okay, the directivity D is equal to the maximum radiation intensity, that is P average into R square divided by the average radiation intensity. Average radiation intensity is total power R divided by 4 pi. You have to remember these two things. Okay, then you can compute the directivity of any antenna. For short dipole antenna, I know the P average value and the total radiated power. Here I have given PR. Okay, don't confuse about this one. No? Here R indicates also is radiated total radiated power. This is watts. Average power is in watts per meter square. Okay, we have to. If you want, you can write here. PR indicates total radiated power. Okay, don't worry about that notation. You have to clear about that units. Okay, therefore, the directivity of the star dipole antenna this is equal to 3 by 2 times of sine square theta maximum. Okay, since the maximum value of sine theta is equal to 1, okay, you can write this equal to 1.5, or if you convert this into decibels, okay, it comes 1.76 dB. Okay, in previous question paper they have asked this question. Okay, show that the directivity of the short dipole antenna is equal to 1.76 dB. Okay, for that what you want to remember, you have to remember the average power and the total power. If you know the, if you remember these two equations, okay, you can able to answer this full question. Okay, 6 marks question this one. Okay, now we want to discuss the radiation from the half dipole antenna and a quarter wave monopole antenna. Okay, normally a dipole means what? It has a two poles. Okay, this is one pole and this is another pole. Okay, a dipole antenna is a symmetric antenna. Okay, see, let us say this antenna is placed in a z direction. Okay, z axis. Okay, this is the z is equal to 0 axis. Z is equal to 0 axis. This antenna is symmetric about this z axis. Okay, here for this dipole antenna, okay, we are assuming that the currents in this dipole antenna, like the current distribution in dipole antenna is in a sinusoidal way. Okay, the current distribution in dipole antenna is a sinusoidal waveform. Therefore, here we are considering a small portion of this antenna. Okay, due to this small portion of this antenna, okay, from the distance value we'll try to calculate the vector potential. Okay, in any antenna derivation, okay, what we will do is first of all we will find out the vector potential. Will calculate, that is a bar. Okay, from vector potential, if you know the vector potential, from a bar we can able to calculate the magnetic field intensity. What is the relationship between magnetic field intensity and vector potential? That is equal to H is equal to del cross A, or curl of A is nothing but the magnetic field. Okay, if you know the magnetic field, okay, how to calculate the electric field intensity? If you know the H, E can be easily calculated. How to calculate the E? That is equal to from curl of H. Okay, integrating the curl of H, we will get the electric field. This is the same procedure. If you take any antenna, first of all we have to find out the what is the vector potential. From the vector potential you can able to find out the magnetic field intensity. From the magnetic field intensity we can find out the electric field intensity. If you know the magnetic field intensity and electric field intensity, we can able to calculate the average power. From the average power, you can able to calculate the maximum power. If you know the total power or total radiated power. Okay, if you know the average power and total radiated power, you can able to compute the directivity of the antenna also. These are the procedure we will follow. But different antennas are there having different formulas that things you have to clearly you have to observe here. Okay. Here, half-wave dipole antenna, which is a symmetric antenna, okay, the length of this antenna is half-wave. Half-wave in the sense, if the length of the antenna is lambda by 2, what is the length here? L. L is equal to lambda by 2. That antenna is called half-wave dipole antenna. Okay, let us assume here it is having a one arm here. This is the length of this arm is plus h, and this is a another arm here. This length of this also plus h, but it is placed in the minus h direction. Okay, here the current distribution is represented as Im sin beta h minus z. Here Im is the maximum current. Im is the maximum current in that direction. Here beta is the phase constant. Okay, phase constant. Because of this length of this h, the phase will be varied. What is the phase? Phase beta is equal to 2 pi by lambda. Lambda is the wavelength. Okay, for this plus h dipole antenna, okay, the current distribution is in the form of Im sin beta h minus z. Similarly, for this side minus h, okay, the current distribution is Im sin beta h minus, sorry, h plus z. This one is, you have to change this one. Okay, I have forgotten to change this one. This is h plus z. Okay, you have to remember. Okay, similarly, here I have want to make one more point here. Okay, the radiation pattern of this half wave dipole antenna and quarter wave. This is a quarter wave monopole. Monopole means it has only single pole. Okay, single pole means it has only one arm, one pole. Okay, the other pole is not here. But the other pole is, here it is connected to the perfect ground. Okay, here the length of the antenna is lambda by 4, quarter wave. Quarter means lambda by 4. The length of the antenna is equal to lambda by 4. The type of antenna is called quarter wave. And also it is having only one pole. That's why it is calling as a quarter wave monopole antenna. Okay, here you have to remember that, you have to understand that the radiation pattern of half-wave dipole and quarter-wave monopole antenna both are having the same radiation pattern, but one difference is the radiation resistance is if the radiation resistance of this half-wave dipole antenna is capital R, okay, the radiation resistance of this quarter-wave monopole antenna is R by 2. Okay, that is the main difference. Rest of the things are similar. Okay. Okay, here I will consider a half-wave dipole antenna and we'll try to solve first the vector potential, and from the vector potential we'll try to calculate the magnetic field intensity, and from magnetic field intensity we'll calculate the electric field intensity. Okay, let us assume here some one distant point is there. Okay, here I have given actually here these things I have to write it down in the other here also for half a dipole also. Okay, here we have an observation point P, that is in a far field. Okay, in that far field we have to calculate the vector potential at the observation point. Okay, let us assume this is the center of the this is the center of here we are apply the source to this antenna. Okay, in this figure you can see this is the center actually. Okay, from here to the observation point it is representing here. Okay, similarly if the current element if it is here, okay, if you want to observe at this point, you can say that these two lines are similar, but if comparing to if the source is here and if the source is moved to here, okay, because of the change in this, okay, uh, the waves which are coming from here and reach the observation point, and the the wave fields that are emerging from here and coming to this point, there is some small, the path difference is there. Okay, that path difference here, this the theta is the polar angle here. Okay, actually here this also theta, both are same. Okay, if you see that this is the length of the infinitesimal small portion of this conductor. Okay, small infinitesimal volume, you can say. Okay, suppose if it is dz, if it is having current I into dz is the total current here. Okay, I into dz. Okay, here first of all we have to find out the vector potential at the observation point based on this I into dz. This I is the current passing through this, and dz is the uh, this is the distance here. Okay, dz. Okay, how to calculate that one? Initially here, first of all we will find out the conduction current density. From that conduction current density, if you integrate from integrate minus h to plus h, we will get the entire conduction current density. Okay, we'll see step by step how to compute this one. Okay, here the dipole antenna is a vertical radiator and it produces maximum radiation in the plane of normal to the axis. What is the axis? This is the axis. Okay, maximum radiation is in the normal to this axis. Okay, in some textbooks, okay, you can see the the current distribution is continuous and you'll get maximum here. In some textbooks you'll get like this. Okay, don't worry, both of them are correct only. Okay, here the length of this antenna is capital L, that is equal to 2h, and here this is the length of this is h, and this is length of this h is also h. Okay, here figure 1 and figure 2 I mentioned that here it is a half wave dipole antenna and it is the quarter wave monopole. Monopole means single pole, and the length is lambda by 4 here. Here it is lambda by 2. Okay, for the current element I into dz, okay, is placed at a distance r from z is equal to 0 plane. Okay, let Im be the maximum value of the current in the current element. The current for z greater than 0, for z greater than 0, this is the z greater than 0, this is z less than 0. Okay, here based on this phase constant, we can write for z greater than 0, this equal to I is equal to Im sin beta h minus z. Similarly, for less than 0, I is equal to Im sin beta h plus z. Okay, now the differential, this is the general way of representing the the differential vector potential. Okay, you have to remember this formula. Okay, the differential vector potential is in the form is equal to mu into I divided by 4 pi r into e power minus j beta r. Okay, in terms of the phase constant, we can represent this formula. You have to remember. Okay, this is the differential vector potential. Okay, here we have the how to from the differential vector potential. Okay, we can able to compute the vector potential. That is equal to, we will integrate this vector potential. See, actually, due to this small differential volume, we are finding out the differential vector potential. Okay, we have to consider the entire region. Okay, if you take this half wave dipole, okay, from minus h to plus h, okay, you have to compute the vector potential. For that purpose, you have to integrate from minus h to plus h. That's why we are writing here. Therefore, so from here onwards, simply I am substituting all the values only. So see that equation. So in that equation. Okay. Now the vector potential A is equal to mu by 4 pi. We have to integrate this uh, this differential current here I into dz. Okay, this integral minus h to plus h. Okay, I by r into e power minus j beta r into dz. Okay, we have to integrate with respect to minus h to plus h. Okay, for the current value I, for z greater than 0 it is having one value, for z less than value it has another value. There is some phase difference is there. Okay, now substitute I value in the equation 2. Let us say this is our equation 1 and equation 2. Now substitute equation 1 and 2 in equation 3. Okay, if you remember this equation, you can able to easily derive this one. Okay, now substitute here. What will happen? See, you can integrate this first minus h to 0 and again 0 to h. Okay, that's why you can write this vector potential is equal to mu by 4 pi. Take this mu by 4 pi as common. Integral minus h to 0 I by r d power minus j beta r dz plus mu by 4 pi integral 0 to h I by r e power minus j beta r into dz. So substitute here now for minus h to 0, that is less than 0, z less than 0, is equal to im sin beta h plus z. Same, you can write this. For the z greater than 0, z greater than 0, the I value is equal to im sin beta times of h minus z into dz. Now you have to, okay, now you have to integrate with respect to dz. Okay, here we have to make some assumptions. Okay, actually here this r is the distance where we are measuring the at the observation point. Okay, there is some path difference is there. Okay, we are whenever we are talking about the far fields. Okay, because of the far fields. Okay, these two lines they are parallel. Okay, because of the far fields, we are assuming that okay, that little path difference is there. We will minimize that little path difference and we can make r is equal to small r is equal to capital R. This thing you have to understand. Okay, we will change it only in the denominator only for reducing the complexity of this problem. Otherwise, you have to write r is equal to capital R is equal to r minus z cos theta. Okay, here in the denominator we are replacing capital R is equal to small r, and the numerator we are replacing r is equal to r minus z cos theta. Okay, this thing you have to remember here. Okay, for our mathematically simplification purpose. Okay, we are doing this one. Okay, it doesn't affect any much of the uh, that performance or the equations. Okay, that's why we are assuming this in the denominator we are using capital R is equal to smaller because we are considering about the far fields. Okay, numerator we are writing the same r minus z cos theta. Okay, okay, here in this here also here capital R is there. There you have to substitute r is equal to r minus z cos theta. Now here now substitute capital R is equal to r minus z cos theta in the numerator and substitute capital R is equal to small r in the denominator. Okay, we are getting this expression here. Now we want to simplify this. Okay, how to simplify this one? Here we are integrating with respect to dz. That's why we are keeping the dz term inside and remaining all other terms are outside of this integration. What is the dz term? We have a e power j bz cos theta term is there. E power minus j beta is also is not a, there is no z term, right? You can bring it out. Okay, you will get mu by 4 pi r im e power minus j beta r into, will get this equation. Now Here some sin beta times of h plus z is equal to sin beta h plus beta z. That is equal to sin. What is this beta? Beta b is equal to 2 pi by lambda. Okay, this is the phase constant. We already know the phase constant beta is equal to 2 pi by lambda. Okay, you already know that one. Okay, here the length of the h is equal to what? What is the h is equal to? H is equal to what is the h? H is equal to L by 2. What is the length of the dipole antenna? Lambda by 2. L is equal to lambda by 2. H is equal to L by 2. Therefore, Emma, are you understand this one? We want to calculate the beta multiplied by h. What is h? H is equal to L by 2. What is L? What is L? Length of the dipole antenna. L is equal to lambda by 2. L is equal to lambda by 2. Therefore, h is equal to, you can write h is equal to, what you can write? H is equal to, h is equal to lambda by 4. What is beta? Beta is equal to 2 pi by lambda, right? This is equal to 2 pi 2 pi by 2 pi by lambda into what is the value of h? H is equal to lambda by 4. Now substitute here. H is equal to lambda by 4. Now b into h is equal to, now this lambda and lambda will get cancelled. Now this 2 and 2, b into h is equal to, now you will get this is equal to pi by 2. You will get the pi by 2. This is the pi by 2. How we are getting? Dear students, are you able to understand this one? Hello. Dear students, are you able to understand this? Now, are you able to hear my voice? My voice is clear or not? Dear students. Okay, ma. Okay. Okay. Okay, please try to concentrate here. Ma. Okay, that's why b into h is equal to pi by 2. Okay. Okay. Now substitute b into h is equal to pi by 2. Sin pi by 2 plus bz will get cos bz. Similarly, here also cos bz will get. Now substitute here cos bz into e power j bz into z minus theta. Similarly, here I want to change here minus h to 0. Okay, by changing the here by multiplying with minus j. Okay, replacing z is equal to minus j. Okay, you will get, okay, you can interchange this and you can write 0 to h cos beta z e power minus j beta z into cos theta into dz. You can write here. Okay, after that, next, see here, same equation I have written here. This is e power minus j beta z into cos z. Here j beta z cos theta. Now cos beta z is the constant. That's why the limits are same. That's why we are writing in a single equation. Here e power j theta plus e power minus j theta, okay, divided by 2 is equal to, okay, we can say cos theta. Okay, what is theta here? Is equal to cos bz cos theta. Okay, e power j theta plus e power minus j theta divided by 2 is equal to cos theta. See here, this therefore this equal to 2 times of cos theta. What is theta? This is equal to 2 times of cos bz cos theta into bz. Now, see here, this is 2 cos A cos B, which is looking like 2 cos A cos B. This is equal to cos A plus B plus cos A minus B form. We were writing in this formula. Okay, it's a simplification here. Further, you can write that this is cos of bz if you take the common bz into 1 plus cos theta plus cos of bz into 1 minus cos theta into bz. Now, now we have to integrate this with respect to dz. Okay, integration of cos is equal to sin theta, and again you have to integrate this internal also will get, therefore we have to differentiate with respect to z b into 1 plus theta. That's why we are getting here. Here also, here it is integration of cos bz is equal to sin bz 1 minus cos theta, and again you have to differentiate this one, that is b into 1 minus cos theta. Okay, that's why we are putting here. Now the limits are 0 and h. Now you have to replace the z with 0 and z with h. Okay, now here I am doing some simplification here. Okay, what is the simplification? Taking the LCM and multiplying with the 1 minus cos theta. Beta and beta I am bringing out outside of this parenthesis. Now multiplying 1 plus cos theta into 1 minus cos theta is equal to a plus b into a minus b. A plus b into a minus b square minus b square. 1 minus cos square theta, that's equal sin square theta. Here, in place of z, okay, sin 0 is equal to 0, sin 0 is equal to 0, that's why we are getting the only this h term is there, minus 0, this is 0. Okay, now beta h, we get beta h, in place of z, we will get the h term. Now, what is the value of beta h? Just now we have computed, that is pi by 2. Okay, now you can write this is 1 minus cos theta is there, no, right? This 1 minus cos theta into sin pi by 2. We have to be very careful here. This entire term is one term. This is another term. This entire sin beta h, this is a one big term. Okay, be careful. This is sin, this is pi by 2 into 1 plus cos theta plus here 1 plus cos theta into sin pi by 2 1 minus cos theta. Okay, now we can, if you take this pi by 2 inside, you will get sin pi by 2 plus theta plus pi by 2 cos theta. That is nothing but cos pi by 2 cos theta. Here also cos pi by 2 cos theta will go. Okay, further if you simplify this, here cos pi by 2 cos theta, cos pi by 2 cos theta is the constant. Okay, and here 1 minus cos theta, if you multiply these things, okay, all terms will be get cancelled. We'll get cos, here 1 is there, no, if you multiply this here 1, this one will get this term and this term will get cancelled. You will get 2 cos pi by 2 cos theta sin square theta. This is the AZ value. See, entire this derivation, okay, is based on the simple assumption here from dz and getting the AZ. There we are substituting the I current values only. Okay, from this here we are getting this expression. Okay, now if you know the A value, what is the A? A is the vector potential. Now what is the time now? How much time we have for class? 2:10. We have left with only 2 minutes. Okay. I will explain this one. Here also del cross A bar. Okay. Del cross A bar. From del cross A bar, we will compute the magnetic field intensity. Okay. Here B is equal to mu into H pi, that is equal to del cross A of phi. Okay, H is having the phi component. Okay. For the phi component, we have to calculate this term, right? R into sin theta divided by R square sin theta. What is the phi term? You have to omit this column and this row. Dou by dou R of R A theta minus dou by dou theta of AR. Okay. See here, since electromagnetic wave is traveling in the R direction, okay, in this case, electromagnetic wave has only H phi and E theta. AR is also 0. Okay, you have to remember this thing.